Hello, everyone. I am Janelle Thomas, a third-year biological systems engineering scholar from Palm Beach, Florida, and I attend Florida A&M University. Today, I'll be presenting you my presentation on field mapping and characterization of the magnetic field profile of a thin steel ring on a 9.4 Tesla magnet. So basically, what did I do this whole semester, this whole summer? Basically, I focused on the development and use of like a custom steel ring to analyze and correct the magnetic field of an NMR magnet to make sure we see optimal field homogeneity or field uniformity. So some of the project objectives would be validate and potentially improve the Romeo and Holtz expression, which basically is used for magnetic field correction, and understand like the deviations in the magnetic field, and also understand what might be the causes for these deviations, and as well as enhance the use of passive shims and address inaccuracies over longer trajectories. So, magnetic field correction, why is it important? So some magnets actually require both rough and fine fields. And so some magnets are actually not built or, designed for like NMR use, and they actually do lack some like built-in rough correction. So that makes the design a little bit more or less efficient. And basically field correction is super important because it improves accuracy, and also it helps to make the results of the experiments being run more accurate as well. So there's different kinds of shims. And basically, there's passive shims, superconducting shims, active shims, and what are we doing kind of today or discussing kind of today would be like the ferroshim technique, which is basically like a low-tech method for magnet field correction. And so basically today, or what I did during the presentation, sorry, not during the presentation, but during my couple of weeks here was I mapped, and I actually mapped the magnetic field. So basically, it's really important to calculate or like calculate the magnetic field. And basically what essentially mapping is you basically create impulses around the sample, and it basically measures points of the volume. So in figure 2, you guys can actually see how you guys can see like the sample, like the ball, and then, in mapping, it essentially goes all around in little points all over the sample. And so you guys can see that in figure 1, this is actually like the sample size, which is so tiny. It's like literally so tiny. You guys can see that. And for us, we necessarily didn't use the sample to tell us anything about the sample. Like, we didn't use the magnetic field to tell us about the sample. However, we switched it in reverse, and we used the sample to kind of tell us about the magnetic field, if that makes sense. So we necessarily didn't really like look at the properties. We weren't looking at the properties in the actual sample, but we were using it to help us with the magnetic field. Okay, so mapping and all the things that we did in the experiment. So basically we can go to the custom steel insert. So for this custom steel insert, it was super hard. We actually, you can actually see right here at my cursor, you see that there's like a little line, but it's actually like a steel ring that's 1 millimeter. And what we did was we did like a solid ring design. Now there's multiple shim patterns, as you guys can see in figure 4, that tell us and help us with generating certain like fields, or not fields, but certain shapes, or it cancels out certain like orders. So for example, like in certain shims or whatever, you see that sometimes if I use like maybe a different ring, then it will cancel out a different order, first, second, third order, and things like that. And so basically what we did was we moved this steel insert up and down in 1 millimeter increments to observe the changes in the magnetic field, right? So and in the setup, you guys could see this is figure number 2 that we see this magnet. This is the magnet that I worked on, and then you can see the cords. And basically these cords are attached to the magnet and it goes to this field regulation. So you guys can't really see it, but so from figure 2 to figure 3, you guys can see that these cords will be attached to this right here. And so this is a field regulation rack. So basically it works, and this is also connected to the computer. So it basically works to kind of communicate from the magnet to the computer, essentially. And so there's different approaches in mapping. We mapped at like a 3 centimeter trajectory. And basically trajectories it kind of refers to the length or extent of the path or with like which measurements are taken. So sorry, various mathematical approaches to the magnetic field exist. And basically these calculations help us create correction shims for different dimensions, including like X, Z, X, Y planes. So in the results, this is the results. So, after we ran all the experiment, the data was processed, analyzed, and plotted, and the results closely aligns with the theoretical predictions of this figure right here, figure number 3. So this is the expressions of the field generated by a solid ring. And so basically this is kind of like the ideal. In figure 1, this is the ideal strength right here. And then in figure 2, this is actually our experimental measure, like the data we got from everything. And as you guys can see, like it looks pretty similar to what we see in figure 1. However, we did notice that Z4 component was slightly off, and me and Dr. Litvak was like, like maybe this is due to like trajectory issues. So we tried to attempt like longer trajectories, but we did face coding software issues. So we weren't able to like do the longer trajectories. But yeah, so our experimental procedure kind of really matched the ideal gradient strength. So to conclude, this project demonstrated the importance of precise field mapping and correction in the magnets, and the custom steel ring and experimental approach really helped us into like just kind of validating Holt's equations and further seeing why, and later we can actually go into see what are the issues or like what are the discrepancies or deviations that we're seeing in the Z4 component. So some of the discussion topics that we can probably go into would probably be like the ways field correction helps performance and help enhance performance in NMR magnets, as well as the role in the trajectory length and how that plays within the accuracy of field correction. So with that being said, I tried to get everything in 3 minutes, but thank you guys for watching. Oh, yeah, thank you guys for listening.